screen. All right. So first and foremost, he's probably going to ask you on the exam. It's a very common question to give you a molecule and ask you how many signals there are. And signals is really just it really just means how many unique environments there are. So first and foremost, you want to check if there is a line of symmetry, and there is down the middle. And you'll see environmentally, these hydrogens on this methyl and these hydrogens on this methyl are in the same environment because of this symmetry. These hydrogens will appear as the same signal in the spectrum. So I'd just like to label as 1 and 1. All right. And as you know, carbon can only hold 4 things, and so there's an implied hydrogen here, implied hydrogens here. So this is a hydrogen of itself. There's nothing symmetrical about it. So that's your second signal. These two are symmetrical to each other. So you have 3 and 3. And lastly, your fourth. So if you're given a molecule like this, and it just asks you how many HNMRs, how many unique environments are present in this HNMR molecule before. All right. Moving along, similarly, you have this line of symmetry here. You have these implied hydrogens, and you have these methyls. Due to this line of symmetry, all of these are the same, right? And these two methyls are the same to each other. So 2 and 2. So in this structure, you have 2 HNMR spectrums. And he could ask you for carbon, but you're going to really focus more on that in organic chemistry too. But just in case, you would do the same exact thing, except you would disregard the hydrogens and just count for carbons. But anyways, environmentally with this one, these hydrogens on these two methyls are in the same environment. So these are its own signal. So you have 1 there. Oh, here comes the noise. You have your implied hydrogen here. It's its own environment. Here's your second signal, and it's implied. But going back to your functional groups, you should know that this is an aldehyde, as there's an implied hydrogen here, and that is your third HNMR spectrum. Signal. Right. This one is very similar to the first one. There's no hydrogens here. Oops. No hydrogens here. There's hydrogen there. There's similarly, right? And there's 2 hydrogens here. So these hydrogens on these methyls, due to the line of symmetry, are in the same environment. They appear as the same thing. So this label. Mom, can you grab the toy? Stop, Mom. Just grab the toy and do something with it, please.
Come here, you can't have that. Michael's teaching. Come here. Come here. Get over here with that toy. You gotta drop it. Mommy got you another one.
Please hurry, Mom.
You want the big Rottweiler to bite me?
Yeah, I do.
Kitty.
So again, because of this double bond, these due to this double bond, if it were a single bond, you would know that these hydrogens are sp3, but they're not. They are stuck in that conformation, and so this hydrogen is the same as this, and this hydrogen is the same as this, and here is its own signal. I'll tell you why when that'll make more sense when I get to these. So the big difference between these two is this cis and trans. And so again, as usual, these two are reflective and they appear as the same thing. Here's your implied hydrogen. Like the key is these down here. So just as a visual, all right, so there's your, just drawing it in another way. And again, this is that carbon is sp3 hybridized, so one of the hydrogens could be wedged, another could be dashed. You don't have to do this. This is just for explanation purposes. So here's your methyl, here's your H. This H, I'm just going to put a plus and minus. This H plus is on the same side of the methyls, so it will feel these methyls as well as these have hydrogen clouds themselves. So even though that there's two hydrogens here, they will each have their own individual signals. So 3 and 4. Unlike the trans, your hydrogens don't really, they're flipping back and forth because of the chiral center, and due to one being wedged and one being dashed, they're interacting with the methyls and appearing as one signal, compared to both methyls being on the same side. So this will be 1, 1, 2, 2, and 3. All right. So far, is counting signals okay? I'll take it as a yes. Moving along, chemical shift. Chemical shift is really just the placement of the peaks on the spectrum. So you're given a spectrum. You're given a spectrum from 0 to 12 for hydrogen, and it's in ppm. Right, that's kind of irrelevant, but you have upfield and downfield. Right, downfield is associated with de-shielding. All right, and what does a shield do? It protects you, but hydrogens that are de-shielded are left vulnerable. Right, they have less of a shield, and that's what something like a halogen will do. The halogen is electronegative, right? And so, for example, this aldehyde, this carbonyl is pulling electron density towards itself and away from this hydrogen. And so there's less electron density to protect this, and so it's de-shielded, and this signal will appear downfield on the spectrum. Right? And so with that in mind, you should be able to reason this. And for chemical shift, this is really, it's again, just the position of the signal on the graph or on the spectrum, whatever you want to call it. And these are the categories. So your carbonyls, it's always, that's what's going to de-shield the, it's going to de-shield the hydrogens the most, as opposed to your alkyls and double bonds that are simply just dude, this kid has had trouble since day one. Or simply just carbons, and there's nothing to de-shield the hydrogens from. So that's as much as you need to know, really. Multiplicity, this is probably second most important to counting signals. So the rule you're going to have to remember is this n+1 rule. I don't know if there's a name for it or anything like that, but it is what's most important. And it comes down to the relative environments. So coming off of counting signals, this environment is different from this environment, right? And so looking at these hydrogens here, this is the neighboring environment. How many hydrogens are in this neighboring environment? 2. So for this signal here, 2 plus 1, okay? Because N is the amount of hydrogens that are in the adjacent environment. So this methyl here, the hydrogens have 2 neighboring, these are neighboring, there are 2 of them here. The 2 plus 1 is 3, and you're going to see that often called a triplet. So singlet, doublet, triplet, and so on. So this signal here, how many neighboring hydrogens does this signal have? 3, 4, 5, 1. How many neighboring hydrogens are there? For this one. No one. All right, so there's 5, right? Because here you have 3 over here and 2 over here. So 5 plus 1 is 6. So this signal here will have 6 peaks. All right, and this signal here will be a triplet, right? Because it has 2 neighboring hydrogens from over here. So 2 plus 1 is 3. In other words, it'll appear as a triplet. You're going to get it in organic chem too, but it's not something to worry about now. Hydrogens, the NMR won't split through halogens or other heteroatoms. So this neighboring hydrogen is off by itself. So if it doesn't have any neighboring hydrogens, 0 plus 1 is 1, and that's a singlet. All right. Moving along. Again, just like our counting signals, your unique environments, environmentally, these hydrogens are the same. So how many neighboring hydrogens are there? None. There's no hydrogens on this nitrogen, and regardless, the NMR can't split through this heteroatom anyways. So 0 plus 1, please, Mom. 0 plus 1 is 1. In other words, it is a singlet. So these hydrogens here will appear as a singlet, or one peak, right? And these here are really just the same as this example. So just like this one, environmentally, these are the same, and they have one neighboring hydrogen here. So it is going to be a doublet. 1 plus 1 is a doublet. 1 plus 1 is 2. Up here as a doublet. Right. This hydrogen has a lot of neighboring hydrogens. Has 6 from these methyls over here, and it has 2 from over here. So it has 8 neighboring hydrogens. 8 plus 1 is 9. So that this hydrogen, this one hydrogen will have 9 peaks, and really anything above a 4, he's going to call it a multiplet because it just gets too much. So it'll appear a multiplet. We often just designate as an N. Right. So there's other ones, but for here, there is 1 neighboring hydrogen. So 1 plus 1 is a doublet. This one, there is 2 neighboring hydrogens. So it is 2 plus 1 is 3. It's a triplet, and so on. So does getting multiplicity make sense so far? All right. And integration is the least of your worries. It's the ratio, or if you've taken methods of calc or calc, you know that this kind of really means the area under the curve, and so it really kind of just it really is the ratio of hydrogens and what type of and how many types of hydrogens are giving off what kind of signal. And so, for example, again, this is the least of your worries. So, just as an example, these 3 methyls are in the same environment. How many hydrogens are there? There's 9. Right. And so, just to give you a visual, you're going to have a peak here. Let's just call it A. Right? This one here, this signal has 6 hydrogens. Let's just call it B. And this one here has 3. And let's just call it C. So because the integration associates, it's just the ratio among them, so relative to each other, and in turn it corresponds to the height of the peak. So like this example, so like 9 divided by 6 is 1.5. So you're going to have another peak that's with this ratio relative to this. I know I'm struggling to explain this, but so like 3 divided by 6 is 0.5. So your C signal will be half of your B in terms of height. So if you can somewhat visualize it, you can see that the number of protons kind of associates with the height of the peak. Does that kind of make sense? And I'm going to run a little bit over time with this next one. But you're going to be given multiple choice for it. But as an example, what is it? Here. You could be given a spectrum and asked which structure is correct. And for this one, I'll just give it to you and walk through it after. So all right, so based on the spectrum, we are given the IR and NMR. So regardless of IR and NMR, what I would do is find the degree of unsaturation. And if you were to plug the formula, or if you were to plug the atoms into the formula, you would get that there is a 4th degree of unsaturation. And if you remember correctly, that is associated with a benzene ring being present. And we have that here. Next, there's this singlet here. There's this singlet at around 2.3. The singlet, remember, there's no neighboring hydrogens, so which this methyl will be our singlet because there's no hydrogens next to it to split through, and so this will be your singlet. So there's no neighboring hydrogens. You have this doublet here, and again, going back to our multiplicity, n plus 1, how do you get a doublet? You have one neighboring hydrogen, and so you should be able to see that. Nope, that's wrong. Here, these environmentally are the same, but they have one neighboring hydrogen here. And so 1 plus 1 is 2, and so these here will appear as a doublet, as you see in the given NMR. It'll turn out to be a septet because like this example here, you have 6 hydrogens and no other neighboring ones, so 6 plus 1 is 7, so it's going to appear as a big multiplet, which matches up. Okay. And the rest are simply your basic CH aromatic, which would, again, you should be able to see with the IR. Again, that's as complex as it's going to get. Again, in bonding, it'll be harder because you're not going to, because you might not be given multiple choice. But in your lecture exam, that is how you would go from spectrum to narrowing down to your correct structure. So if there's no particular questions, that is all I have for you today. regarding NMR. So I'm going to go ahead and stop